So these again these are some of the challenges that we still have open to work with this persistent memory technology. What do we do then? We'll look into different ways of accessing persistent memory and some of the cutting edge researches that propose a solution to some of the challenges that we discussed about. But in order to understand that, first we need to understand how persistent memory DIM. Now, as we proceed, we are discussing more and more about persistent memory as a memory, because practically thinking that makes the most sense. If persistent memory provides an advantage of access latencies similar to DRAM, then it makes sense to have it sitting next to DRAM, right? Why would we want it sitting on a PCIe bus, same as an SSD? That is possible, and we have seen that does pretty good, but from research point of view or from engineering point of view, because it's already doing pretty good, we do not have many challenges to discuss there or to do there. We do not have much opportunities to improve that further. It's just the technology. We are using an existing interface of PCIe bus, the existing IO stack, just to use that, and it's working good. So as it is, if you find a use of that, then good enough. But what we see is persistent memory DIMMs, they are technically, they seem more better in sense of the promises that we get from them, but we are not able to see the performance yet quite there. So that gives us this ray of hope for more opportunities to solve some of the challenges. And that's exactly what makes this discussion interesting. So that's why we will be dipping our feet now more and more into persistent memory as a DIMM form factor so that we can utilize the byte addressability of it directly from CPU. Now, how does persistent memory DIMM or Optane DIMMs in particular interact with other system components? So as we see here, we have integrated memory controller that maintains the CPU queues. Now we have the persistent domain, inside which we have our Optane DIMM. Inside Optane DIMM, definitely we have 3D cross-point storage media. So that's the place where actual data is stored. But apart from that, we also have some memory. As we have seen until now, most of the smart devices are computer system, small computer systems by themselves. They would have some compute power, some memory, and also the persistent storage capacity, right? So in the same way, we have some DRAM. Why would we need DRAM? Is because as we just saw that we have this little table sitting over here, which is translation table, where would we store this translation table? If we store it on the persistent media, we are in this translation table is accessed pretty heavily. For every IO that we want to do on device, we would have to access this translation table. So it makes sense to store this translation table on a faster media than the persistent storage. And definitely we can maintain either battery backed guarantee of reliability, or we can maintain like a persistent copy of this. So there are different methods, same as what we do inside SSDs. Similar methods could be applied over here. So we have this DRAM to store the translation table, and we have controller that can consist of different buffers, because we saw that the write and reads are done at the cache line granularity of 64 bytes. But physically inside the 3D cross-point media, the data is stored at the granularity of 256 bytes. So it makes sense rather than having a read modified write for every possible write that is lesser than 256 bytes. It would make sense to have a buffer where if a write size is lesser than 256 byte, we would store that write here temporarily. We would wait for some another write, second write to come. And once, as soon as the size is equal to 256 bytes, we could put that into the persistent media. So now that we understand how persistent memory interacts with our memory controller, let's see what are different access methods to use this persistent memory. So there are two currently most popular methods for accessing persistent memory. First, block access. So definitely these persistent memories could also be used as a traditional block device. So with the block access, persistent memory would operate like a storage for application compatibility. In this configuration, data flows through the file system and storage stack as normal. So if we have an Optane SSD, we could use Optane SSD, which is still using 3D cross-point technology. It's a persistent memory in a block access with a block access method. When we use persistent memory with a block access method, then we can use this configuration in combination of any popular file systems like NTFS, REFS, and it is one of the most recommended use, or it's one of the most used way for Optane SSDs as of now. But a more interesting way to use Optane memory DIMM would be direct access using DAX. So how does the DAX direct access work? It operates like a memory to get the lowest latency. And if we don't use, the risk here is if we don't use DAX correctly, then there is a potential of data loss. So with the technology like Optane memory DIMMs, we could definitely use that under this access method of direct access, but then it's upon the operating system stack or application to ensure that we make correct use of that. Otherwise, the data may not be persistent because we just don't know how to make it persistent or how to use it in this persistent mode. Now for Intel Optane DC persistent memory modules, there are two most popular ways. Well, there is one more, which is mixed mode, which is combination of this both that you see on the screen. But if we know what those two components are, then we can always mix, right? If you know what is vanilla ice cream and what is strawberry ice cream, and if you want vanilla, 1 scoop of vanilla and 1 scoop of strawberry, that's always possible. So what is this individually? What is this vanilla ice cream and strawberry ice cream? Well, my mouth is already watering, but let's replace vanilla and strawberry ice cream with memory mode and app direct mode. So what is this memory mode and app direct mode that are provided by Intel to use persistent memory DIMMs, to use persistent memory DIMMs in these modes when we install it into our systems? In memory mode, application sees this volatile memory pool, which would, in a traditional system, it would be just the DRAM, right? But now it is memory pool because it's DRAM plus the persistent memory. And with no change to an application, we could use this persistent memory DIMMs in this mode. What is an advantage of using this mode? Well, And ease of using, definitely yes, because we don't have to change anything to our application. Second, physically now we have much larger memory than what we initially had with just the DRAM. So as initially we saw some of the application that desires this huge data set, it wants this data set into the memory to be able to complete the application execution. For such an application, this type of deployment mode provides an advantage of capacity at an affordable cost, with an assumption that our opt-in persistent memory DIMM costs us less than what DRAM would cost. But what is a disadvantage of such a mode? Is there any disadvantage? Yes. The biggest disadvantage is we are not using the persistence property of persistent memory. We are just using it as a memory. But it's okay. It's a new technology. Until we are able to identify the best way of using it, at least we are identifying different ways of using it, right? Today, memory mode is one of the most used deployment mode for 3D crosspoint DIMMs. A second, a more practical mode, to me at least, is app direct mode. In an app direct mode, now application, rather than seeing this unified pool of memory, it sees DRAM and persistent memory into its own separate capacity. So now in app direct mode, the burden lies on the shoulder of user or operating system to somehow know how to use this different types of memory that's available to application. If that's not done correctly, then performance by using this mode, or even the correctness of doing something with using this mode, would be questionable or compromised. And another very big difference between these both modes is in memory mode, DRAM is used as a cache for persistent memory. So let's say if we had 16 GB of DRAM, and if we had 128 GB of persistent memory, because now this DRAM is used as a cache, the memory that's exposed to the application by if deployed in a memory mode, that is just 128 GB. So we are losing whatever is the size of DRAM because it just becomes the cache to persistent memory. But in app direct mode, if we have 16 GB of DRAM and if we have 128 GB of persistent memory, then the amount of memory that's visible to the application is the sum of both. So the total, which it should be, right? So app direct mode, although a bit more challenging to use, has some potential of being able to extract or do more better if done correctly. Recalling different ways or advantages of using memory mode, or just different facts of memory mode. The persistent memory and DRAM are fused into single volatile memory space, as we see here in the pool. Because DRAM outperforms persistent memory, DRAM is used as direct mapped write back cache for persistent memory. Now, we learned that DRAM is used as cache, but did any one of you had a thought in your mind why it is used as a cache? Why not the other way? Why not using persistent memory as a cache for DRAM? Will it make sense? Well, we want to use a media for cache, which is faster than the other media, right? Otherwise, what's the point of making it a cache? And we know that DRAM is faster than persistent memory. So it makes sense this way, DRAM being used as a cache for persistent memory rather than the other way around. And also capacity here plays a big picture. We want to cache the important data in the media into a faster media. So definitely if there is 100 items stored in the media in total, out of this 2 are important, then we just want to cache this 2. So cache can be smaller or much smaller compared to the entire media's actual size. So in this case, we can have much smaller DRAM, larger persistent memory. It fits the best. Now, a very important thing that should be noted here is that in this mode, we are not using the persistence characteristics of persistent memory. And why is that? Because for data security, the data in persistent memory is internally cryptographically erased between 2 different power cycles. So at each power cycle, it will be cryptographically erased. And that's just how the memory works. And that's why, even though the media physically allows us to process the data, but every time we reboot the system, that data will be gone because of such a mechanism of erasing. Easy way to use large capacity, but does not take an advantage of persistence. Yes, we understand that. Finally, reduced total memory capacity. So as we just discussed earlier, that in this mode, because DRAM is used as a cache, with the example that we saw earlier, we are losing that 16 GB that DRAM provides as its own capacity. Now it's only 16 GB in our example, but a real system can have really huge DRAM. So imagine like that is no longer could be considered as a usable memory. Revising our facts about app direct mode. Persistent memory are exposed to system as permanent storage devices in app direct mode. So now applications could see DRAM and it as well as the persistent memory both together. Persistent memory on the same CPU socket can be grouped into an interleaved group. So we can extract parallelism. An interleaved group is very similar. You can visualize that as a RAID 0, where you stripe the data across different entity that we have, which increases the bandwidth by that data striping mechanism. It provides persistence and does not use DRAM as a cache. So now we are no longer losing the DRAM's capacity. Plus, we do not have that intentional cryptographic erase that we had in the memory mode earlier. So the data that we store in persistent memory in app direct mode could be persistently saved, but again, it depends upon the user or the operating system to how to take advantage of this persistent data. If operating system or user is not taking advantage of persistent data, then there is no point. So still we would have this capability of persistence, but we are not taking use of that. So app direct mode provides a mode to use the persistence, but again, it could be still, there are different applications which we would soon see where we could use app direct persistent memory in app direct mode, but still not use the persistent property of persistent memory. A file system or other management layer, such as memory tiering mechanism, provides allocation, naming, and access pattern to persistent data. So as we just said, that how to take advantage of this persistent memory is upon user or operating system. Now, in order to take advantage of persistent memory, this mechanisms, we need to have well-defined mechanisms that knows where to allocate data, how the naming conventions of how to manage the data and how to access. If we want the data to be persistent, then even after a crash, how to be able to re-access the data that we want. So using persistent memory as fast storage devices, one of the very popular way to use that is by deploying a file system that is particularly designed to take advantage of the properties provided by persistent memory, such as low latency, low access latency than other storage media, such as SSDs and hard disks, and byte level access granularity. So these file systems, some of the examples of these file systems are, you could see here on the screen, where we have BPFS. What does BPFS do? It can process fine-grained atomic updates to non-volatile memory and provide good performance with strong reliability. If you're interested in learning more about each of these file systems, then it is just a single Google search away. We should have these research articles online in their respective published repositories. So if it's an IEEE paper, it should be available by IEEE Access libraries. If it's a Usenix conference, then Usenix follow the open access to everyone. So it should be available online. The PDF as well as the presentation should be available. So definitely you are most welcome to search it, find it, read it, and learn more. But these are just the very brief advantage of these file systems. PMFS provides a lightweight POSIX file system that can enable direct access by applications and provide fine-grained logging for consistency by utilizing processors paging and memory ordering features. Then one of the currently most popular one, to the best of my knowledge, is NOVA and its variants. The NOVA file system uses the techniques of log-structured file systems to provide a separate log for each file's inode, and thus exploiting fast random access of non-volatile memory. We saw that non-volatile memory, such as the ones designed using this 3D crosspoint, particularly that technology, they're much better than others while for random IOs. So NOVA file system, depending upon this hypothesis that they're faster for random IOs, it has different mechanisms. It proposes different mechanisms to leverage and take advantage of this property in a better way. Then there are some more advancements of NOVA file system, which is NOVA Fortis. It's a version of NOVA, as the name says, that provides greater reliability with snapshots, checksums, replication, and RAID 4 parity protection. So when we are talking about persistence, then definitely all this thing matters. Finally, we have the DAX versions of some of the popular file systems that we use for block devices, such as ext4, XFS. So we have ext4 DAX, XFS DAX, all this persistent memory versions of them. So these are just extension of an original file system that enables us to use persistent memory DIMM in app direct mode.